today's is one of those days, but we are here and ready to go. Nikki Burnett here. Today's Taste Life Nutrition radio and podcast streaming live on kuhsdenver.com, where we are continuing our series on longevity, on toxic load, on all of these amazing things that can help us live this really amazing optimal life that we are put here to live and enjoy and, work our tails off. That's what it's all about. Have some fun and work hard. And anyway, I'll stop there. Thanks, Douglas, for joining us again for such really amazing conversation. Appreciate you so much.
Nikki, it's nice to see your feathers. Are you going to fly away in the middle of the show?
I might. Henry just told me. Henry is the owner of KUHS Denver. He said that my, what'd you say, my Indian name is Yellow Feather?
Okay,
Nikki
great.
Yellow Feather.
Well, right, mine is Spot on Nose right now because your spotlights is in my nose, but just ignore it.
Yeah. We're in it. This is a new studio, fairly new studio to us.
Just call me Spot.
Yeah, Spot.
Yeah, that's my right. That's my indigenous name, Spot.
Well, we're always trying to figure out the spotlight.
On screen. Spot on screen.
Yeah, spot on
Yes.
screen. There you go. Anyway, so we've had some really interesting and enlightening and intriguing and fun conversations regarding, heart health, elastin. What is elastin? I think Douglas will get into that in just a minute, and for a recap, and all kinds of things to open our minds, open our hearts to what it is that we can do to feel good and to live well for as long as we're here. That's really so much of the goal. So, but before we get started, as always, we start the show with gratitude. So, Douglas, what are you grateful for?
Well, actually, I'm grateful that an old friend of mine from 33 years ago showed up on the doorstep yesterday. And it's great to see him again with his new family, and it was just so delightful. The last time we met together, he was doing a documentary film on the work we did on cleaning wastewater in Brazil. Oh. And so this is really sort of an appropriate time for him to show up. They've got this huge camper parked in our backyard here. It's really nice. It's just fantastic to see him and his family. So I'm really grateful for that.
That is so cool. I love that. I love having friends. And you're going to end up talking and having great conversation and hopefully moving forward with other things that you can do. So I think, I don't know if I said this last week. I don't remember, but I think that's what I was. A few years now, and we are in this place, my husband and I were in this place where we are excited and everything, when you have these projects, things get, you have to deep clean. So we've been painting and laying tile and baseboards and all of these sort of things that are outside of what we normally do. But we're getting them done and it looks great and we're having fun with it, and I'm excited it's almost like you're in a new house. So I like that. It just feels really good. So grateful, super grateful for that and for moving forward with the to-dos that have to be done. So let's do just what you had said. Let's do a little bit of a recap of the last 2 weeks, and we'll just move on from there.
Sure. So you talked about elastin. I'm not going to go through the whole thing, but because people can watch and listen to the show. But elastin drives every breath you take and every move you make. Hardly anyone knows about it. It's not the collagen that most people hear about. Collagen makes your body stiff and strong, but it certainly doesn't make it flexible. And it's the elastic fiber that is woven in between all of that collagen that actually gives you all your flexibility, and it's also the stuff that falls be up shortly on your channels, right?
Yeah, so we have, I shared it yesterday.
Cool.
The second one
Great.
will probably be uploaded this week, and then this one hopefully next week. So kind of depends on how we move through it. But yeah, they'll all be there, and I need to share it with you.
Was about what harms those elastin fibers, and what you can fiber that normally starts to fall apart in all of us after we reach the age of 25 or 30. And that we talked a lot about heavy metals and the damage that they do. Today, we're going to be talking about the actual stuff, the tiny nanometer size stuff that drives both of those processes, both keeping your elastin healthy and making it sick and tearing it apart. But, Nikki, it does far, far more than that. It is what we are and what we are on this planet, and amazingly, most people have never heard of it. And the really incredible story is that women scientists are leading this new field. And this is what makes it doubly exciting, because many scientific fields have been traditionally dominated by men, and especially this type of cellular research where it comes to heart disease has often been led by men. That is completely different here. And so we'll be talking about the role that women scientists are playing, and we'll be talking about the Cuban Revolution that no one has heard of. And that has very much to do start sharing my screen and hope that this all works, so everyone can bear with me and let me see here. So can everybody see that?
Got it. Yep.
Okay, we are cool. Okay, so I'm going to describe this picture in a minute, but the name speaks for itself. Exosomes. What you are looking at here is on the left-hand side for most people, and I'm describing this also for the radio audience, is the membrane of a cell. And out of that membrane is coming these tiny little particles. They are between 10 and 100 nanometers compared to millimeters for cells. And the stuff in the upper right-hand corner, we're going to be talking about in a minute, is what is inside those little things. Now, I call this the FedEx of life. And we're going to learn about, we're going to learn about that in just a moment. But these exosomes are us. They are us, they are animals, they are vegetables, they are part of our universe, they're part of our water, and they're part of our air, and hardly anyone has heard of them. And they are not passive, they are programmed. So we'll get into that in a moment. Hit the forward button. The other one never works. Okay, so this is a rendering of an exosome. Keep in mind, what you're looking at here is the diameter 1/1000th the size of a human hair, just about. And what you're looking at here is a double-walled membrane that is made up of lipids and fats and a few other things. And inside it, and this is a cutaway view, so a half view, the exosome cut in half. And inside it are proteins and RNA. And this RNA that instructs your DNA sort of what to do, that's a simplistic way of putting it, but this RNA was only discovered in these exosomes about 12 years ago. So it's quite a new discovery. Now, the interesting thing is that this is really a lab on a chip. That's what I call it. Why do I call it a lab on a chip? That's because when cells create these tiny little particles, they actually custom package these mixes of different proteins and RNA, and they're all custom made to do a specific task that cells themselves are too big to do. And we'll be talking about that in a moment. And when the cells push these things out into the space around cells, which we call the extracellular space, it's the space between your cells, and it's the biggest space in your body, just in case people are wondering, well, yeah, okay, the space, but it's actually the biggest space in your body is the space between your cells. So in that space, as these exosomes travel to their destination, there are chemical reactions going on inside. They have been programmed to actually do things as they go, and they gather other proteins and RNA from that extracellular environment. It's an astonishingly complicated and really amazing process, especially since for about 50 years after they were discovered, scientists thought that this was cellular garbage removal. They thought that cells just packed the stuff they didn't need, into here to get it out of them. And then, they were excreted, out through the kidneys and, through your pores and everything else. Well, turns out that that's about 1% of the truth. They do serve, 1% of them or less serve as garbage collectors, but the rest of them drive every single activity in the human body. Every single activity through this extremely complicated combination of these proteins and this RNA, and they do it by going from one cell into a target cell. So they actually have little spikes on the surface of them that make them attractive to specific other kinds of cells. Okay, so that's enough of the science there, but just to show you that here are these literally trillions of these labs on a chip running around your body. Now, these chips are not only programmed to be a lab on a chip as they're traveling along and gathering stuff, but they're also, oh, and there's one important thing I forgot to say. I should have said it at the top of the show. Nikki, because your show is so much about nutrition and food, this stuff, food is made of this stuff. Single vegetable, plant, whatever, it's full of these exosomes. So just, that's the relevance to nutrition, and hardly anyone has explored that in nutrition. It's really amazing, but we'll come back to that. So what you see in this picture for the people listening is a cell, and these little dots on top, the little blob on top of the cell is an exosome, and these little things inside it are actually labeled to proteins in the cell so that they can track them. And you can see these labeled little dots going into the cell. That's exactly what exosomes are programmed to do. They're not only programmed to be labs on a chip, but they're programmed to travel around, find their destination cell, and be accepted into the cell without an immune response. This is very, very important. It means the cell recognizes them as being friendly. That works both for and against your cells, because guess what? Some very nasty things in your body have figured out to play a trick on your cells and actually use this same mechanism to attack it. So this is really a Dr. Jekyll and Mr. Hyde. It's the same kind of Dr. Jekyll and Mr. Hyde we talked about with elastic fiber. It's really great when it works, and when it doesn't, it starts to age you. Well, this is the same thing here. So these are all used to defend your body against infection and all those kinds of things. But on the other hand, bacteria and viruses use them to attack. So you can see how this is at the heart of us. This is at the heart of living beings, exosomes. And again, there's trillions of them in, a square inch of your body. There's an amazingly huge number of them. So, for example, and you see this again for the people listening, it says viruses hijack exosomes. That was discovered in 1955. So you'll quite often hear that the coronavirus is an enveloped virus, right? That's what it's enveloped. Well, guess what it's enveloped in?
Exosomes.
It's enveloped in these exosomes. And so why is that? Because the exosomes are recognized as friends by cells. So these viruses hijack the exosomes, hide inside it, and that is how COVID gets into your cells. So you can see how terribly fundamental this is to health and disease. And this has been known since the 1950s. Really extraordinary.
It really
Just
is.
stop.
Go ahead.
Yeah, stop. You're going. Go ahead.
Okay. So this is also interesting to me, and I want to give a little bit of my own background. I'm a conference nerd. I love to go to conferences, but there's one in particular that I will always hit every single year, no matter what. And it was probably 3 years ago that they brought up this. Well, and so I'm gonna say this as they say it. Essentially, this is not my expertise. But what I find fascinating about it, as how you explained exosomes, is that the virus is actually enveloped in the exosome, whereas what they would say is, sorry to docs out there, but virology has never been proven, and that the what a virus is actually an exosome and not a virus, because nobody's actually ever seen.
You are exactly right. There's now a huge argument on over the chicken and the egg.
Right.
Yeah.
Exactly.
That's
and
perfect.
So
good for you.
Yeah. It's fascinating stuff, and of course it's it's the things that we don't hear much about and that we don't know much about. Well, I think there are a lot of people like you who do know a lot about it, but to say that a part of the medical community is based on what has never really been proven, that's a hard thing to talk about, and I totally get that. but it is what it is, right? And that's, to me, that's what science is about. What true, real science is about is, okay, every day we learn something new. This is what life is about. We learn new things. We prove and we disprove, and we prove and we disprove. And to put blinders on about something like this, as hard as it might be to not have the blinders on, but is really problematic. And so we have to, in my humble opinion, be open to sometimes we're wrong. And I think a lot of times we're wrong. And so I say this, I've talked to you about them before, and I talk about Cellcore all the time, but this is the conference that I go to where they talk about these things that are cutting edge, that are outside of what we know to be true today. I mean, the things that they bring to our attention they've been mind-blowing to me, and this isn't the place to get into it, but they're the ones who talk about the interstitial space that needs to be addressed and detoxified, and they go after that space, and they talk about the exosomes and are there truly viruses, or is it the exosomes? And so these would be people probably you would be interested in chatting with, I'm sure. But
yeah, sure.
This is
and you Nikki, you mentioned the interstitial space, which is what I called, and you used the more scientific name, it's also called the exosphere. But it's the space between your cells, and I'm so glad that you used that name, because just a few years ago it was named the 80th organ in the body, and it is the largest organ in the body, the interstitial space.
Mm-hmm. Yeah, it's fascinating stuff, and again, we continue to learn and build upon what we know, and sometimes things are disproven in the meanwhile. But to know that we've had this thought in our history that there are things in our body that don't matter, right? The appendix doesn't matter. The interstitial, space or interstitial tissue doesn't matter. The fascia doesn't matter. All of these things have a job and are there for a reason. And I think that we don't credit the body with as much beauty as it is. And we're like, you don't need that, or that doesn't matter, or it's fine, And what we're learning is every single piece, every cell, everything has a job, has multiple jobs, and communicates with each other. And to have this assumption like, wow, it's just not there, it's just there for just to look pretty or whatever, it's amazing.
Or it's just a garbage collector.
Yeah, exactly.
this simplistic view, you know.
That's exactly what it
it's a
is.
garbage collector.
Yes. There's so much, nothing about us is simplistic. Nothing about our universe is simplistic. And to make things simplistic is really problematic. So anyway, go ahead. This is fascinating stuff.
No, that's a great point. You know, you obviously you know a lot more than you know a lot of people know, so that's cool. Okay.
A lot I don't know.
Yeah. So what we're looking at here, again, I'm narrating for radio as well. The exosomes also play the role of an internet for cells. What that means is that they let cells communicate, and the picture that you're seeing here is of these exosomes tethered to each other and connecting cells together. Mm-hmm. So these exosomes not only help cells communicate by traveling between cells and carrying information in between, but they actually physically connect them, Nikki. So there's these two different ways of doing this. And to give you another example, they control every thought you have. Mm. Why is that? Because your neurons exchange a type of exosome that helps you think. So this is really, you know, affecting every part of your body. This is really a remarkable photograph. I mean, this is down to, you know, like 10 nanometers. And so the huge things in the picture are the cells, and the small ones that these are really the internet for cells in a very big way. So now the story, one of the stories, exosomes are being used for therapy and very, very successfully used for therapy. And amazingly enough, the first time that they were used for therapy was in the 1980s. Now, in the 1980s, no one was talking about nanotechnology. No one was talking about nanometer-sized objects except people, you know, in the electron microscope area. And in Cuba, hundreds of thousands of children were getting sick, and many of them were dying from what many people know to be bacterial meningitis. And around the world, hundreds of thousands of children were dying from different strains of the disease. Now, as you know, Cuba had a problem. There was an embargo on everything going into Cuba from the West. So they had to build up their own science, and Fidel Castro did, most people don't know this, he did a really amazing thing. You know, he's obviously controversial, and he did a lot of bad things, but this is one really, this is really one smart thing that he did. He took all their foreign currency and he bought laboratory equipment. And that was the birth of Cuba's biotech industry, and that was like in the 1960s and 70s. And so what happened was there was a group of women scientists at what is known as the Finlay Institute, which is an institute based in Cuba. And they were preoccupied with this problem of these hundreds of thousands of children getting ill from bacterial meningitis. And everywhere in the world, no one had a solution to it. But it was a big deal, especially in Cuba, because this was a particularly nasty variation on this bacterium. So they started working on it. And what they discovered was that the antibodies that allowed you to develop resistance to it were not in the cell itself, they were in the exosome. Mm-hmm. So the cells were packaging the right proteins and RNA into the exosomes that provoked immunity. So what they did, amazingly enough, in the 1980s, is they isolated these exosomes and got enough of them to be able to inject them and develop this immune response. And they were so confident of it, and they're not the first ones to do this, lots of medical researchers have done it, they infected, sorry, they didn't infect themselves, they tested the vaccine on themselves.
Oh, wow.
And some people are going to be horrified to hear this, but they had no choice at this time. They vaccinated their kids. There was, there's no mouse model for this.
Yep.
So after doing all of the in vitro tests and pretty well feeling that this was not non-toxic, they injected it. And lo and behold, their kids and they had immunity to the disease.
Wow.
So this was a team of women scientists in Cuba, and what's really incredible is that years later, the capitalist world's intellectual property organization, which is called the World Intellectual Property Organization, awarded its gold medal for intellectual property to what's known as it's known as the membrane vesicle, OMV, outer membrane vesicle, which is a very long word for exosomes. It's a different type of exosome,
Okay.
so it's called the OMV vaccine. And even more amazing than that, one pharmaceuticals company in the United States got special permission from the US government to license the vaccine for the United States.
Interesting.
And that indeed is what they did. And the result of that whole thing today is that there is a global campaign based on this vaccine, and Novartis, that a lot of people have heard of, a drug company, actually licensed the thing and put in a combination of vaccines that come from around the world so that people were immune to all of the combinations of the vaccines. And if you look at the history books, it says, well, Novartis pioneered this vaccine. This is nonsense.
Unreal.
This is really a bad piece of history to be telling, because it is not true at all. This was pioneered, developed, tested, and manufactured in Cuba. They actually, anyone who's been in biotech, I'm the co-founder of a biotech company, knows that scaling up from the lab to a market-based vaccine or treatment is very challenging. That's the reason that penicillin took 2 decades to actually get anywhere, because they didn't know how to scale it up. And so that's exactly what they did, all on their own, without any help.
Wow.
So they started from zero, invented the vaccine, discovered that the exosomes had it, invented the vaccine, then tested it, then scaled it up, then had it licensed worldwide. And today, that same group, the Finlay group, along with other groups in Cuba, have more than 100 patents to their name and are a biotech powerhouse. And this was all led by women scientists.
Fascinating stuff. So I'm curious. I think I'm curious because I have, as I've aged and as I've learned more and as I've paid more attention, not everybody's going to agree with me, and that's okay. Everybody has their place. But I've become more and more, I find vaccines to be more and more problematic. Now, with that being said, I'm very curious about the vaccines that are these exosome vaccines.
Yeah, the answer to your question is this is a naturally derived vaccine.
That's what I was wondering.
It wasn't synthesized.
Okay,
and that's one reason it was so successful, because the exosomes are accepted into cells.
Right.
So they didn't genetically engineer it.
Okay.
They didn't futz with the proteins. They didn't do any of that. All they did was they refined so that they basically got the exosomes, and they proved that you can create an immune response with them. That was it.
Okay. Are they being used today?
Yes.
By Novartis, they are.
It's called the OMV vaccine, and it is very well known. And there's a consortium of countries around the world whose goal it is to wipe out bacterial meningitis by 2030. It's a phenomenal story.
Okay. That's awesome. I love that. I think this what can be so problematic with vaccines too is just the adjunct junk.
We'll be talking about in just a moment. It's being used for cancer therapy. I mean, just think of it. Exosomes are so readily accepted,
Mm-hmm.
into cells
Sure.
that it just makes sense to, to load them for targeting.
Yeah.
Now, that's a different level because you are then, you're putting stuff into these exosomes, but you can also just refine the natural characteristics of them. So I'm going to tell the story. So the answer to your question is they're being used for developing therapies for cancer, and they're being used for developing heart disease therapies. And in particular, at two universities, one at Harvard and the other at King's College in London. There are two women researchers who are barreling ahead with this. They've spent 20 years on it. Professor Elena Ikowa is at Harvard University, and she is specialized in which one of the proteins that are in these vesicles, and I'll have to go back a step and explain this, that trigger heart disease. Now, why did she do that? Because in 2007, she discovered that it actually was these exosomes that are triggering the early inflammatory response and the calcification that leads to hardening of the arteries. She's the one who proved it.
Wow.
And she did it with new technology, near infrared, which actually allows you to peer, a few millimeters below the skin. And she was actually able to image these things in real time. That's what she did. And actually her paper in 2007 was awarded Paper of the Year by Circulation. So, and of course no one's heard that either. But it was truly a remarkable discovery, and someday I think she'll really be recognized for this amazing discovery. So then her team, and by the way, Elena, who's a good friend of mine, I did a documentary film on her, on calcification. She was not just on her, but on the whole thing of calcification many years ago. She has one of the most fantastic laboratories overlooking the campus at Harvard University. It's just unbelievable. And I have to say this, because a woman designed the lab, you're not in the basement under fluorescent lights like a lab rat. Right? There's floor to ceiling windows, and I mean, it blows you away to walk into this lab and see, wow, it's actually designed for humans to work in it.
And you want to be in it.
You want to be there. You want to be there. And so, that just shows credit to her and the different perspective I think that women can, bring to these professions. So she's absolutely one of my favorite people, and she's a full professor at Harvard, and she's a medical doctor as well. And so what happened was that her team started looking at, okay, what exactly is in these things that is triggering this hardening of the arteries or this calcification? What makes the calcification happen? And what they discovered is that there's a number of key proteins that do that. And so what they figured out is how to actually inhibit the production of those proteins. When they made that discovery, there was one of the largest pharmaceutical companies in Japan, and Elena's husband, Professor Aikawa, is Japanese actually, and he knew this company is called Kowa. Anyone in the pharmaceuticals industry will tell you, Kowa is one of the biggest pharma companies. And he and Elena did something really extraordinary at Harvard. It took them 3 years to do it, but they created an active collaboration between Kowa Pharmaceuticals and Harvard. Now, you would think, these days that, oh, that's easy and universities collaborate with big, nasty pharma, all the time. Not so. Believe me, I speak from experience. And collaboration between universities and pharma companies is tough work. The universities they react against it. The IP departments don't like them. It's a real problem. And that's one of the reasons that therapies are so slow to come to market, because of this gap between discovery and scale up, because of this management gap between the universities and pharma. And, so they bridged that gap. And now Kova is actually working on this therapy right now as we speak. So here you have another phenomenal development driven by women. And then you have Catherine Shanahan, Professor Catherine Shanahan at King's College, and she's doing work very similar. She's also looking at the types of proteins that trigger calcification, and her work has been actually licensed by a small startup company that works with Cambridge University. So they're taking another, instead of going with a big pharma company, they're going with a sort of an incubator company. And so that is going on. And they're good colleagues, you know, Elena and Catherine, and they've co-authored some papers. So here you have really talented, hardworking women who have fought their way to the top and are driving this vast new area of science. And I cannot overemphasize how huge the role is that exosomes play in everything, You know, they're in our water, they're in our air, that's how plants grow, they're in our food, you know, so it's a huge, huge area, and it's being driven by women.
So I want to go back to the hardening of the arteries real quick, because
Sure.
and I don't want to get too deep into this. Anybody who has interest in this, I did a podcast on, you know, cardiovascular disease and cholesterol and that kind of thing. And so where we are today, well, and hopefully we're moving away from it, but we blame cholesterol, right?
Yeah.
Cholesterol is the problem. It's what's packing up our arteries, and that's where, you know, we keep having these cardiovascular issues and these events and so forth. And we keep saying this and we keep treating the cholesterol, yet we still have constant events, constant heart attacks, constant strokes. This is happening all the time, and it's not getting better. And so we're still going after cholesterol. We're still filling people up with statins. We're affecting so many parts of the brain and our muscles and our productivity by feeding people statins constantly. unnecessarily, and we're not addressing the root cause. So,
and by the way, statins provoke calcification.
Yes.
Lots of studies that have shown this.
Yeah. So
why would you, and the mantra was, well, you know, if it provokes calcification, that stabilizes your arteries. Let me understand this. By hardening your arteries, no, really, that's a very serious argument by these guys, you know, that hardening of the arteries actually protects them. Well, what Elena Aikova proved was nothing can be further from the truth, because the way that these are formed is with these nasty, spiky little pieces of calcification that are physically and chemically toxic. Yeah. And they are created by the deposition of chemicals from these membrane vesicles, the types of vesicles that you see on the right-hand side of the screen here. And guess what? That damage is happening not in the so-called lumen, the place where the blood flows. That's not where it starts. You know, they always talk about how heart disease starts with the buildup of cholesterol in the arteries. Nothing could be further from the truth. In most cases, not all, but in most cases, it starts in the wall of the artery, you know, really in these layers, where, by the way, elastin fiber is located, and that's one of the first things to get injured. Yep. And these vesicles are at the heart, if you'll pardon the pun, of the whole thing, because they get in there, because they are the response. So when elastin is damaged, it sends out the help signal, help, I've been damaged by heavy metals, whatever, and the cells manufacture these exosomes that are full of inflammatory proteins to create an inflammation process that is intended to repair the artery. But guess what? The elastin fiber continues to deteriorate because it's continually damaged. And your body is not replacing it after the age of 30. So this stuff starts to grow and pile up. And then guess what happens? Then the inflammatory stuff starts breaking through the wall into the blood, the area where the blood flows, which is called the lumen. And guess what the wall of these little exosomes are made of? Fat. So, you know, and so what what these statins are trying to target, and what they're talking about when they talk about reducing cholesterol, is not the point about reducing cholesterol, because 50% of the people who have heart attacks have perfectly normal cholesterol. It's what your body is doing with that cholesterol. But this stuff here in these exosomes is actually, it starts being the fatty buildups. But that's long after the disease has taken hold in the wall of your artery. So you're quite correct. We have been barking up the wrong tree, that's for sure.
For sure. Yeah, it's going back to, and this is what I have, it's constantly unwinding the story that we've been told for, however many years. And again, going back to, we have to look at science and look at our own research and understand that as we grow, the data changes because it gets better, and we have to stop going after cholesterol. We have to start going after inflammation. Going back to what we talk about, right? What I talk about all the time is, what is the root cause? What is causing the inflammation? Because it's the inflammation that's creating the problem, but we got to understand what it's from, right? So you go back to, is it the heavy metals? Is it stress? Is it the unhealthy
all of the above?
Yeah,
all of the above, and it's called, all of them cause injury. Injury.
Exactly.
And again, it was Elena Ikowa who identified the injury, inflammation, calcification cascade. That's what it's called. The injury, inflammation, calcification cascade. That's what she identified in 2007.
Yeah, it's fascinating. And I hope that anybody who is listening to this is really paying attention. I have a lot of really good resources. They don't talk about exosomes, but they talk about heart health and cardiovascular health and cholesterol, and what cholesterol actually is. And we have to have cholesterol. We can't just cut it out, because this is how our cells function. This is how our brain functions. And so, if you're being told you need to be put on a statin, I would highly suggest that you dig a little deeper and figure out the why behind it. And it's one of those things that really frustrates me, because it is again going back to being simplistic to say that HDL is good and LDL is bad. It's the most damaging, simplistic version of cholesterol that there is. And half the time I see people come back and they've been told that they need to be put on a statin, half the time, maybe most of the time. I'm looking at their lipid panel, which is just a couple of lipids and no inflammatory markers. They don't. I'm like, what? How can we look at cholesterol and look at any part of the body and dysfunction and not look at inflammatory markers? That is the key to so much of it, if not all of it, is the inflammatory markers, understanding where and why there's inflammation, and then going after that.
Yeah, anyway. And having said all of that, just a rejoinder here, and that it's that in some cases, statins in combinations with other drugs in people who have had heart attacks or something like that, they can be beneficial. So I don't want to, paint them all with the same brush, and everyone has to talk to their doctor about it. So I'm not saying throw the stuff out the window by any means. You do need to talk to your doctor about it. But as you said quite correctly, get a second opinion from someone who knows a little bit more about diving into cholesterol. Yep, that's for sure. And now people know from listening to this program that that's how you get this fat buildup. And so it's quite a sophisticated process, and it has been well on its way before any of these fatty deposits show up. First you get the injury in the wall, then you get the inflammatory response, you get the degradation of the elastin fiber, then you get the beginnings of the calcification much earlier than most people think, because most diagnostics can't detect it. And all of that's going on before you get the buildup. Sometimes you will get the buildup starting in the lumen, but it's usually because the endothelium, which is this single cell layer that protects the wall, is damaged. And it's chronically damaged. It's even chronically damaged by red blood cells bumping up against it. But if it gets bad, as it does in a lot of us as we age, then you can get this buildup. So it's not 100% that the damage always happens in the wall, but most of the time that's what you're looking at, and most of the time it's not detected.
Right, totally agree. And I do want to go back. There's one of my favorite people who I've done a lot of research on, or a lot of his reading, is Dr. Stephen Sinatra, who is a cardiologist.
Oh yeah,
yeah,
absolutely.
He's amazing, and that's one of the things that he'll say is, if you've had a cardiovascular event, he will put men, not women, but he'll put men on statins. And so, agreed. Drugs have their place without a doubt, and I am not opposed to drugs. I'm not opposed to all statins. I am opposed to the overuse of drugs that are really harming people. So, but yeah. Anyway, wanted to throw that in there because there are times where it probably has its place. But we have these amazing scans that we can do. The calcium score scan that we can look inside the vessels and have an understanding of whether there's buildup or not. And if there's buildup, you got to address it, right? But you got to know how to address it, and you've got to address the inflammatory response that's happening underneath. So,
and you don't even the calcium score is a really good way to go, but there's something you can do that's far cheaper and less. You're not exposed to as much radiation, and that's the CIMT, which is the carotid intima thickness. Okay. And that is the blood vessels that run up your neck to your brain.
Yep.
And a handheld device in the hands of someone who's trained can be very effective in showing, and now people maybe understand why this is so important, how thick the wall of your artery is. Not just what's in the bloodstream, because it also shows up what's in the blood corridor, but how thick, and that thickness, and also whether the surface of the lumen is wavy or it's smooth, like a baby's bottom, as they say.
Yeah.
And so the CIMT is a really low-cost way of getting a preliminary look, and then you can do the CIMT from there, which is usually quite a bit more expensive.
Great. Yeah. Thank you for that. I didn't know that. I want to know more about that.
No, it's a fantastic tool, and it's really amazing how when I was living in Germany, my GP, he used it all the time. Cool. And he tracked me for 10 years, and that was really good news, because actually he didn't see any progression, which was remarkable. We can talk about that on another show sometime.
Yeah.
But I come to Canada, and we only do that in emergencies. And I'm just thinking, what? I mean, this is such a simple and inexpensive. And then you get to see why the medical system is so expensive, because they've got to, yank people into the MRIs and everything else, when a CIMT would be a good first defense.
Yep.
Anyways, it's another story.
Yes.
Let's get to the exosomes.
Do it.
And what we're looking at here is another drug delivery vehicle. And what you're seeing on the screen here is basically a drug-loaded exosome getting into getting into a cell and killing. This is a bad cell. So this an infectious bacterium or a cancer cell, it gets into the cell because it's accepted in, and you can see by this white stuff on the right-hand side, lower right-hand side, the drug is having its effect and is killing off the cell. So this is what we call the Trojan horse. And that's exactly the same mechanism that viruses use. They do the same thing. They envelope themselves in the exosome, and they get into cells. So we're now beginning to use that same tool in order to do this. So this is another example of how the therapy is being used. I just want to talk about how long this has been around. The virus thing I said was 1955, but actually they were still identifying them as membrane encased viruses in the 50s. They didn't know about exosomes. And even though they were seeing them, they saw lots of them, but they just thought, they called it cell dust.
Of course they did.
That's what they called it. It was like for 20 years it was cell dust.
Wow.
What is this? What's cell dust? Yeah, it's around all over the place. We see it all the time. Yeah, no, it's just,
it
it's
doesn't
there.
matter.
Yeah. Then, in 1967, in the United States, I have to say, a colleague of mine made an incredible discovery, and this is H.C. Anderson, the late, great H.C. Anderson. And what you're looking at here on the screen is a whole bunch of fuzzy stuff here, and that's calcification. But it's not calcification in the arteries. This is calcification in bone. So exosomes make bone. Exosomes make bone. So
Cool.
cells pack exosomes with the proteins that actually combine in the extracellular space with other chemicals that then create bone. So all our whole bone structure is created by these vesicles. It's astonishing.
Yeah.
So that was the great discovery. And you know, other people have taken credit for this discovery, but you know, I stood up in front of a bunch of scientists when I was hosting. I was giving the keynote address to one of the first meetings of the International Society for Extracellular Vesicles. And I made a point of saying it was Anderson in '67 because a lot of people claim it was in the 1980s and some other people discovered it, but it was Anderson who did this. He deserves credit. We did a tribute to him there, and I think he's firmly established now as a result of that in medical history. And this is one of the great discoveries in medical science. So, you know, wherever you are, Anderson, we love you. You really did a fantastic thing. So that's how the discovery happened. And then it was discovered in heart disease. Then it was discovered in other things, you know. And there were discoveries made all the way through the 1980s and 1990s about where these things were found. So, question is, why did it take so long? Right? We knew about them. We saw them in the 50s. Anderson discovered them in the 1960s. Oh, and by the way, I have to say, he had a co-discoverer by the name of Bonucci in Italy. But Bonucci just discovered them. He didn't see them making bone. And that was the great discovery, that they're active. So Bonucci is credited with co-discovery. I need to give him credit. So just to be clear on that. So it was a combination of the Italians and the Americans. So the question is, why have they been ignored for so long? Well, here's a really funny story. And you were talking earlier about the hubris of science, right? Well, this is a really good one. So, you know, for decades, scientists were using, and by the way, they still use, for some purposes, a dye called acridine orange. And acridine orange is used to dye cells so that you can see what's going on inside them. And they dye the vesicles because cells are busy manufacturing, you know, these vesicles. So what was happening was the dye was, you know, it was imbued in the vesicles, and then they watched them gravitating out of the cell to the surface and blebbing out, and then boom, they would release their protein and their RNA load into the extracellular space. And so everyone thought, oh, so that's what's happening. They're being packaged into these vesicles. The vesicles make it to the surface. They're thrown out of the cell. And then they magically find their way all through the system. Never mind that they get destroyed in about half a nanometer by, you know, a very aggressive extracellular environment. But that, you know, they overlooked that little detail. They developed the hypothesis that these proteins and RNA magically made their way around into other cells and delivered instructions. Okay, that was an interesting leap of faith. Well, it turned out that when they were observing them with the electron microscope in a Petri dish, the wavelength of the microscope was exciting the acridine orange, and it was exploding the vesicles as they left the cell.
Oh, wow.
And so the whole thing was a disaster. And in about 2007, someone discovered this and they published it. Well, the funny story is that when I was giving a presentation to all the scientists at the International Society for Extracellular Vesicles, the room went suddenly quiet. When I said, well, this happened in 2007, that was like 6 years ago. This was 2013. And everyone started looking at their, you know, their personal devices. And I realized that some of them were still using acridine orange.
Oh, yeah.
And so I didn't get much applause on that one.
Well, again,
You know?
going back to the new discoveries and being open to, maybe I need to change the way I practice a little bit.
Oh, yeah. And this was a big time thing. So quietly, it is now, when they stopped doing that and they started tracking them in other ways, guess what they discovered? They discovered that these are the FedEx of life because they transit their way through the extracellular space and into other cells, and they deliver their program packages. So they're the internet, they're the FedEx package, they're the lab on a chip. What else can I say?
Yeah.
You know, and women are leading the charge on discovering what they are and what they do and how we can use them for novel, safe therapies.
Awesome. So good. Thank you. You just wrapped it all up in a pretty little bow right there.
Great. I don't have my watch on me. Are we out of time?
Yeah, we are. But
Okay,
that's
then
okay. We started late.
Okay. So I stopped sharing my screen so you can see my face again. There I am. And because we're running out of time, here's the book where we talk about exactly that. I do a chapter on Elena Aikawa and Catherine Shanahan's work,
Awesome.
Discovering the Nature of Longevity, Restoring the Heart and Body by Targeting Hidden Stress, a story of great discovery, great therapies, and you know, you can get it on Amazon. It's been on the bestseller list 3 times. And you see those little things, those little circles going around behind the ear there? Well, that's a representation of exosomes.
I love it.
So they're on the cover, and that's why they're there.
Cool. So good. Well, and so everybody who's listening, watching, we will put, all of these links. This is our 3rd in our series and the last, but it won't be the last time we have you on because this has all been just amazingly fascinating. I would love to dig into the cardiovascular stuff with you. But, so his links are there where you can find him, find Douglas, are all going to be linked. I do want to, though, give a shout out. We had Susie on with Vibrant Health last week. Vibrant is an amazing company. I use them almost exclusively for all of the labs that I run. They do functional lab testing. They also do some, your kind of more conventional lab testing, your CMP, that kind of thing, but we can extend them to make them even bigger and better. And so when we talk about cardiovascular health and cholesterol, just looking at your HDL, your LDL, your triglycerides, your VLDL, this is not enough. So we have to look at the inflammatory markers. We have to look at the particle sizes of the cholesterol, not just HDL and LDL. There are like subgroups, subclasses of cholesterol.
Yeah.
These are the things we've got. There's so much that we need to understand to try to put the story together. And these are the things that I use Vibrant for. I use them for my toxin panels, which is what we're doing a special on. So if you're interested in understanding your toxic load, whether it's environmental toxicants, your heavy metals, which can go hand in hand, mycotoxin exposures, all of these things that play a role in the degradation of our elastin, the degradation of our health and our vitality and everything that we are. These are the things that burden the body that it's always trying to fight. So if we're nutrient deficient, it's because the body's always trying to fight. And so let's find out why and then address it and not just cover it up with a drug or not even just cover it up with nutrients, right? With supplements. We want to not cover up. We want to address the problem. So, Douglas.
And it was great to have her on the show as well, talking about their panels for heavy metals.
Yeah.
So yes, shout out to her.
Yep.
Fantastic. I really enjoyed doing the show with Susie, and I hope to do it again.
Yeah.
We can maybe talk about other things.
Yeah. I think we definitely will. I think it'll be a lot of really great conversation. I love digging into the science, and I hope that you love digging into it with me. Tell everybody where you can be found.
At natureoflongevity.com. So that's all one word, natureoflongevity.com. And the shorthand for that, and now people will understand it better, is calcify.com. It's CALCIF as in Frank, Y.com. And that is, of course, what calcification is all about.
Yep.
So there you can find the information about the book and a whole lot more.
Cool. Very good. Of course, you can find me, tastelifenutrition.com, Taste Life Nutrition, and all the socials. You'll find us here every Thursday at 10 a.m. Mountain Time, where we're streaming live at kuhsdenver.com, except next week. I'm taking a break next week. So, but yeah, it's always good to take a little bit of a break. But yeah, if you have any questions, always feel free to reach out. My goal is to be a resource, is to be of service to you in any way that I can. I have an assessment that you can fill out on the website that comes straight to me. We'll chat about whatever's going on with you, and if I can help or if I know someone who can. So you can always find us there.
Nikki, next week, if people are used to tuning into the show, they can tune into this podcast instead.
Yes, they can. Thank you for that.
Yeah.
So yeah, the podcasts are anywhere you find your favorite podcast. So we have, we've been doing this 4.5 years now. So we've got some great ones. But this is our first series, and I think that it was about as good as it gets. So grateful for you and all of your time and all that you're doing.
Well, thank you so much for doing this. This was a really great series. And I'm just going to tell all my friends about it. I just really want to thank you because they all tie together, really, right from the elastin through to the heavy metals, through to exosomes. It's been a great series. Thanks very much.
It has. Thank you for that. All right, everybody. Thanks for joining us. Hey, Cam, good to see you. And we'll see you all here in a couple of weeks. Take care.
Bye.